Hello, my name is John Garrick. I'm a consultant and practitioner in the application of the risk sciences to engineered and natural systems, and I have the pleasure of discussing with you today the risk science known as Probabilistic Risk Assessment, or PRA. Probabilistic risk assessment also goes by such other names as Quantitative risk assessment and Probabilistic safety assessment. I consider them all to be the same discipline. The lecture today is an introduction to just one method of doing PRA, a method that evolved from the famous reactor safety study, sometimes referred to as WASH 1400. The changes from the reactor safety study methodology are primarily in three areas: the adoption of algorithms that better facilitate site-specific applications, the treatment of uncertainty, and the adoption of a scenario-based approach. The method as it has evolved was principally developed by my former consulting firm, PLG, with extensive support from the nuclear electric utility industry. It has been applied to over 40 commercial nuclear power plants in the United States and many more similar plants around the world. This methodology is being successfully applied to many other systems, including chemical, petroleum, defense, space, and transportation. Of course, adjustments have to be made to accommodate the differences in the applications, but the adjustments primarily have to do with simply using different boundary conditions. My approach to this presentation will be to start with a learning objective, present some historical information on PRA, highlight the overarching principles of the methodology, provide a few examples of the form of the results, and close with a summary and conclusions. Let us proceed with the first slide. What I intend to cover in the short time of this lecture is a brief survey of the basic ideas and concepts of PRA. To obtain the capability to apply the methodology will require more study and training by the student. It is hopeful that the references accompanying this lecture will be helpful in that regard. I do believe that the examples at the end of the lecture will telegraph important features of the methodology, such as the general modeling approach and the form of the results. The most important benefit of this lecture will probably be an introduction to the language of PRA, as well as some very basic concepts and definitions. Concepts and definitions that are the signature of probabilistic risk assessment. In particular, our learning objective of this lecture is to develop a conceptual understanding of the important analytical and computational processes of probabilistic risk assessment. Let me start with a few brief remarks about the origins of PRA. When we ask about the origins of PRA, we must ask, why was it invented in the first place? Well, it was invented to put threats having the potential for catastrophic consequences in context with their likelihood of occurrence. It was invented to enable more informed decision-making on how to best manage risk. It was invented to be able to quantify the answer to the question, what is the risk? To answer the question of what is the risk, we really need to answer three questions. What can go wrong with the system? If it goes wrong, how likely is it? And what are the consequences? So what does this translate into? It translates into the fact that the principal task of PRA is structuring what can go wrong scenarios and calculating their likelihoods. In keeping with the triplet definition of what risk is, you could say that risk is scenarios, likelihoods, and consequences. But it is really just scenarios and likelihoods, as the consequences are simply the end state of the scenarios. Thus, when considering the origins of PRA, one way of doing so is to consider the origins of the theory of scenarios and the theory of likelihoods, which we will take to mean the theory of probability. So, what about the theory of scenarios? Unlike the theory of likelihoods that has its origins in mathematics and physics and has developed over hundreds of years, the theory of structuring scenarios has its primary roots in contemporary engineering disciplines such as reliability engineering, failure analysis, and decision analysis. Reliability engineering was primarily developed by the United Kingdom and Germany in the 1930s and 40s. The Germans developed and applied reliability principles to the design of the V-2 missile during World War II. The UK developed aircraft performance criteria based on reliability. Reliability engineering not only developed many analytical methods for analyzing systems, but produced graphical representations that were very useful in modeling how systems perform. Fault tree analysis, a deductive reasoning process for building failure models, has its roots in switching algebra and circuit theory, coming out of the old Bell Labs. It was developed to its present form mostly by engineers at Boeing Aircraft for analyzing missile systems. On the other hand, the inductive reasoning process of the event tree concept has its roots in decision theory and was developed into a systems performance tool in the reactor safety study. Now, what about probability theory, or the theory of likelihoods? The science of calculating likelihoods primarily evolved in the fields of mathematics and mathematical physics and has a history of several hundred years. For example, Cardano and Galileo made important contributions in the 1500s on how to express probabilities and frequencies of past events. Pascal contributed to concepts of decision theory and statistical inference in the mid-1600s. And Fermat and Demir made major contributions to the theory of numbers about the same time. In the mid-1700s, Thomas Bayes, an English minister, developed a theorem rooted in fundamental logic for combining old information with new information for the assignment of probabilities. Bayes' theorem, followed by the publication in 1812 by the French mathematician Laplace of a classic book on probability theory, provided the primary basis of contemporary probability theory. More recent contributors to probability theory include Jeffreys, Cox, Shannon, Polya, Rafa, and Jaynes. What about the most important recent events impacting the development of PRA? Well, everybody has their own list of the most impactful events. Here is my list of what they are. The reactor safety study, of course, for being the first PRA. The Zion Indian Point studies for many new algorithms to facilitate site-specific applications, including the first comprehensive probabilistic containment response models and the treatment of uncertainty. The nuclear utility industry for its sponsorship of the Zion Point studies and its initiative to embrace the PRA concept in plant operations, and of course the Nuclear Regulatory Commission for implementing risk-informed regulations. Key to building confidence in PRA is preciseness in its language. Most of the confusion about PRA really is related to what has become known as the Kaplan theorems, a colleague of mine for over 40 years. Kaplan offers two theorems having to do with the language of PRA, theorems that really apply to language in general. His first theorem is that 50% of the problems in the world result from people using the same words with different meanings. His second theorem is that the other 50% comes from people using different words with the same meaning. Experience has indicated great progress can be made if clear meanings can be given to terms important to understanding PRA, terms that carry a lot of baggage because of different interpretations. Examples are frequency, statistics, probability, and the very concept of what we mean by quantification. This slide provides simple interpretation of these examples that have been very useful. As you will soon see, frequency is a very important parameter in any PRA methodology. This is because, while it is not practical to predict the point in time of a catastrophic event, it is usually possible to calculate the frequency of such events, where frequency is simply a measurement of occurrences per action or unit time. Perhaps the two most abused words are statistics and probability, as they are often used very loosely and sometimes even interchangeably. The interpretation we've chosen to give them makes them distinctly different. In particular, statistics is taken to be the science of handling data, while probability is interpreted as the science of handling the lack of data. Quantification is taken to mean telling the truth about the quality of a measurement, result, or a parameter. That is, present the measurement in a form that clearly displays its range of uncertainty based on the supporting evidence. Thus, quantification does not have to mean extensive amounts of data that can support a measurement out to so many decimal places. That's of course desirable, but a situation that seldom exists. Rather, quantification calibrates the range of possible values of the measurement, given whatever supporting evidence there is. I would like now to discuss some of the fundamental concepts of probabilistic risk assessment. The foundation of this methodology of scenario-based probabilistic risk assessment is something that has become known as the triplet definition of risk. In this definition, R denotes the risk attendant to the system or activity of interest. On the right of this equation, S sub I denotes the ith risk scenario, a description of something that can go wrong. L sub I denotes the likelihood of that scenario happening, and X sub I denotes the consequence of that scenario if it does happen. The angle brackets enclose the risk triplets. The curly brackets are math speak for the set of, and the subscript C denotes complete, meaning that all, or at least all of the important scenarios, must be included in the set. The what can go wrong question is answered by describing a structured, organized, and complete set of possible risk scenarios. The second question requires the calculations of the likelihood of each of the scenarios, and the third question is answered by describing the damage state or end states resulting from the risk scenarios. Now it's time to get a little more precise on what we mean by likelihood. The idea of likelihood can be characterized in reference to the what can go wrong scenarios. If the scenario is recurrent, that is, if it happens repeatedly, then the question how frequently can be asked, and the answer can be expressed in occurrences per day, per year, per trial, per demand, etc. If the scenario is not recurrent, that is, if it happens either once or perhaps not at all, then its likelihood can be quantified in terms of probability, which we will define more precisely in the next slide. If the scenario is recurrent and therefore has a frequency, but the numerical value of that frequency is not fully known, and if there is some evidence relevant to that numerical value, then Bayes' theorem can be used to develop a probability curve over a frequency axis. This is known as the probability of frequency concept and has been a critically important concept in the methodology. Now it's time to get specific about what we mean by probability, another fundamental parameter in the methodology. The chosen definition emerges from what some call the subjectivist view of probability. This view is best expressed by the late physicist E.T. Jaynes of the Washington University of St. Louis. Jaynes says, and I quote, "A probability assignment is subjective in the sense that it describes a state of knowledge rather than any property of the real world, but is objective in the sense that it is independent of the personality of the user. Two rational beings faced with the same total background of knowledge must assign the same probabilities. End of quote. The central idea of Jane's definition is to bypass opinions and seek out the underlying evidence for the opinions, which thereby become more objective and less subjective. So what we mean by probability is, one, synonymous with credibility, as in the credibility of a hypothesis based on all of the available evidence, and two, that it is a positive number from 0 to 1 that obeys Bayes' theorem. Now we address the question, where do we get our probabilities? Scenario probabilities are inferred from all the available evidence using the fundamental mathematical principle of logical inference known as Bayes' theorem. This theorem has a long and bitterly controversial history, but in recent years has become widely understood and accepted. For example, it has been characterized by the best-selling author Peter Bernstein in his risk book titled Against the Gods as quote, a striking advance in statistics by demonstrating how to make better informed decisions by mathematically blending new information into old information. End of quote. Bayes' theorem is the fundamental logic principle governing the process of inferential reasoning. Specifically, the theorem answers the question, how does the probability of a given hypothesis change when we obtain a new piece of evidence? In my opinion, the most striking property of Bayes' theorem is its transparency. It is a two-step derivation from the simple probability product rules. In words, it says that the probability of A given evidence E is equal to the probability of A before you had the evidence times a correction factor. Its transparency is that it is simply one way of expressing the fundamental rules of logic and plausible reasoning. What could be more transparent than that? We have introduced some basic terms, definitions, and the important algorithm offered up by Bayes' theorem. What I would like to do next is highlight the various tasks associated with PRA. Although the scope, depth, and applications of quantitative risk assessment vary widely, they all follow the same basic steps. These steps provide the answers to the three fundamental questions of the triplet definition of risk. The first thing we must do is understand the systems being analyzed and what constitutes successful operation of the system to be able to recognize departures from normal operation. We must then decide what it is about the system that represents a threat to whatever it is we are concerned about, facility damage, health and safety, investment, or whatever. Now that we understand the system, how it works, and what is threatening about it, we now must engage in the creative exercise of developing the what can go wrong scenarios. Scenarios that can lead to the outcomes we don't want to happen. Task 4 is to quantify the scenarios based on all the supporting evidence we can scrape up. The uncertainties associated with the scenarios must be part of the answer, as that is what we mean by quantification. Realizing that we may end up with hundreds or possibly even millions of scenarios, we need to assemble and aggregate them into interpretable measures of risk. Finally, in task 6, we must interpret the results in terms that enable meaningful risk management. This usually means not only presenting different measures of risk, but importance ranking the contributors to risk at a level that provides choices for taking corrective actions to mitigate the risk or reduce the consequences. It turns out that the 6 steps of PRA noted in the previous slide generally collapse into 3 major analytical processes, at least for most physical systems. That is, a PRA basically involves 1, a system analysis that defines the system in terms of what constitutes success. 2, an initiating event and initial condition assessment that quantifies the threats to the system. And 3, a vulnerability assessment that quantifies the resulting risk scenarios and different damage states. Usually the system analysis, the middle part of the diagram, involves linearizing the system into logically progressive operating states. That is, box 1 has to happen before box 2, which has to happen before box 3, and so on. Characterizing the system in this fashion sets the stage for using linear modeling methods, an example of a topic that would have to be covered with additional training. The threat assessment part of the PRA, the top part of the diagram, is a matter of quantifying the events that can trigger a departure from normal operation of the system. This is often done with an algorithm known as the master logic diagram, a sort of super fault tree diagram that deduces the kind of basic events that would have to happen to result in the undesired initiating events. The final exercise, the bottom part of the diagram, is the structuring of the scenarios triggered by the initiating events and the determination of the resulting end states, that is, the consequences. The next question is, how are the scenarios actually quantified? The actual quantification of the risk scenarios is done with the aid of event trees of the type shown. An event tree is a diagram that traces the response of a system to an initiating event, such as a terrorist attack, to different possible endpoints or outcomes, that is, consequences. A single path through the event tree is a scenario or an event sequence. The terms are sometimes used interchangeably. The event tree displays the systems, equipment, human actions, procedures, processes, etc. that can impact the consequences of an initiating event depending on the success or failure of intervening events. In the conceptual event tree shown, boxes with the letters A, B, C, and D present these intervening events. The general convention is that if the defensive action is successful, the scenario is mitigated. If the action is unsuccessful, then the effect of the initiating event continues as a downward line from the branch point as shown in the slide. The scenarios are quantified by propagating the probability density functions representing the split fractions of the event tree through the various paths, constituting the scenarios to their end states such that a probability of frequency curve is generated for each scenario. Now we come to a point in the process where it is necessary to go beyond this survey lecture to provide the details. However, we can note the steps. The previous slide very generally illustrated how the scenarios are quantified. What comes next is assembling the individual scenarios into the aggregated risk of the undesired outcomes and presenting the results in a form that facilitates making decisions about managing the risk. We sketch the assembly process and indicate the form of the results in the next slide. Once the scenarios have been quantified, the results generally take the form of two types of probability distributions. Each scenario has a probability of frequency curve in the form of a probability density function, quantifying its likelihood of occurrence. The curve takes the form of the diagram on the left. The total area under the curve represents a probability of 1. The fractional area between two values of phi, noted as the frequency, represents the confidence, that is, the probability that the frequency has the values over that interval. The probability density function shows the curve for a single scenario or a set of scenarios leading to a single consequence. Showing different levels of damage, such as the risk of varying injuries or fatalities, requires a different type of presentation. The most common form is the classical risk curve, also known as the frequency of exceedance curve, or the even more esoteric label, the complementary cumulative distribution function. This curve, the one on the right, is constructed by ordering the scenarios by increasing levels of damage and cumulating the probabilities from the bottom up in the ordered set against the different damage levels. Plotting the results on log-log paper generates curves as shown on the right. Now, to illustrate how to read these types of curves, that is the complementary cumulative distribution function, suppose P3 has the value of 0.95, that is a probability of 0.95. And suppose we want to know the risk of an x1 consequence at the 95% confidence level. According to the figure, we are 95% confident that the frequency of an x1 consequence or greater, because that's how we structured it, is phi1. The family of curves, usually called percentiles, can include as many curves as necessary. The ones most often selected in practice are the 5th, 50th, and 95th percentiles. A popular fourth choice is the mean. An often used method of communicating uncertainty in the risk of an event is to present the risk in terms of a confidence interval. If the area between a phi1 and phi2 is 90% of the area under the curve, the way to read this result is we are 90% confident, the 90% confidence interval, that the frequency range is between phi1 and phi2. This is about all we can say in this single presentation about the chosen PRA methodology. It is now time to present some examples of models and even results from applying the methodology. The highlights of models and results to follow are from applications to nuclear waste disposal, and from nuclear waste disposal, nuclear power, space shuttle, and acts of nature. Except for nuclear waste, all of the examples are actual results from major PRAs carried to completion. The nuclear waste example is primarily for the purpose of illustrating the linearization process discussed in the last section. This diagram conceptualizes how a PRA model might be structured for a nuclear waste geological repository. Notice the linearization of the system. 5 modules and 4 pinch points provide the basic framework for structuring the scenarios. A pinch point is defined as the interface between modules. Once the output states of a module are defined, then each module can be modeled independently, conditional on the defined output-input states. That is, the modules can be pinched off and worked on separately. The number of both can vary depending on the complexity of the system, that is, the number of modules and pinch points. A single path through all of the modules constitutes an individual scenario from initial condition to dose or human health effect, whatever is chosen as the risk metric. For example, the initial conditions for the non-destructive case to the infiltration module, the first module, could be different climate conditions, and the outputs could be different water compositions, which become input to the engineered barrier module, and so on. Uncertainties of the individual scenarios are propagated through each module to obtain the uncertainty of the whole scenario in the form of a probability density function. Finally, the probability density functions of the scenarios are arranged in order of increasing damage, for example, radiation dose or health effect. Cumulating the probabilities from the bottom up in the ordered set against the different damage levels results in a frequency of exceedance curve of the type discussed earlier. This slide presents 3 of 9 bottom line risk curves that were actual results developed for a specific U.S. nuclear power plant. Results not shown but which were developed include 6 other measures of risk: core damage, plant damage states, release categories, latent cancers, whole body dose, and property damage. While these curves, that is all 9 of them, represent very important results, they were not necessarily the most interesting results to come out of the PRA. In addition to these risk curves, the results included the importance ranking of scenarios, systems, initiating events, plant damage states, and release rates contributing to the risk. A glimpse into the characterization of such results is illustrated in the next slide. This slide illustrates how the results of a PRA can be decomposed to illustrate both sensitivity and uncertainty of contributors to risk. It is very informative to decompose the results into two primary categories of external and internal events. This slide compares the uncertainties, sensitivities, and overall contributions of several external events with the contributions from internal events as a whole. External events are events that are generally acts of nature, although fire can be both internal and external. Internal events are plant-related. Examples are loss of coolant accidents and transients. An important point illustrated by this result is with respect to seismic. Knowing the seismic risk within several orders of magnitude of uncertainty is clearly adequate in those cases where it contributes little to the overall risk, as is the case here. Thus, there is no necessity to do a more detailed calculation, at least with respect to risk. These and other importance to risk contributors were the most useful in making decisions about what corrective actions provided the best return on investment for risk reduction and management. Studies of this magnitude were generally in the few $1,000,000 range and took 1 to 2 years to complete. Where such studies were performed, the many benefits became obvious in the maintenance, operation, and safety of the plant. Let's now turn to a completely different type of application. Here I highlight a result from an application of PRA to critical systems of the Space Shuttle. The systems analyzed were the auxiliary power units of that is the APUs of the Space Shuttle orbiter, and the two hydraulic power units, HPUs, of the solid rocket boosters. The Space Shuttle or orbiter has 3 redundant APUs, and the solid rocket boosters have 2 redundant hydraulic power units, or HPUs, per solid rocket booster. The APUs are critical to all phases of a mission, including ascent, orbit, descent, and landing. The functions of the APU relate to engine control, main engine throttle valve, closure of the 17-inch fuel line, positioning of the main engine nozzles, cooling and heating during orbit, descent flight surface control, landing gear deployment, steering, and braking. The damage states considered were 1. Loss of vehicle, 2. Loss of crew, and 3. Loss of mission. In this analysis, 39% of the loss of vehicle risk came from the scenario involving a hydrazine leak downstream of the fuel isolation valves and into the aft compartment during orbit, and the resulting failure of 2 APUs. Hydrazine leakage and ignition sources could result in a fire explosion in the aft compartment. Hydrazine is the fuel for the APUs. NASA's hazard analysis covered this scenario. 27% of the loss of vehicle risk came from a scenario involving a common cause failure. The scenario was a hydrazine leak from at least 2 APUs concurrently. Leakage location was downstream of the fuel isolation valves and into the aft compartment. Leaks that occur during orbit or entry can lead to catastrophic failure and loss of the vehicle. Early in the program, NASA did not explicitly analyze common cause failures. One of the visions I have for PRA is the quantification of risks by region to facilitate making decisions for how to allocate resources to achieve maximum risk benefit. The next example is a start in that direction. A limited scope PRA was performed that compares the fatality risk of a hurricane landfalling in New Orleans, an asteroid impacting the New Orleans area, and a nuclear power plant accident within 50 miles of the city. While it was no surprise that hurricanes are by far the greatest risk of the regional threats analyzed, it was very interesting to see how they compared when quantified. Some people that have seen these results were very much surprised by the extremely low fatality risk of nuclear power plants, especially the fact that the asteroid risk was several orders of magnitude greater for catastrophic consequences. For this study, catastrophic consequences were arbitrarily established as 10,000 fatalities or greater. The risk of fatalities from hurricanes in New Orleans is much higher than the risk of fatalities from asteroids, which is much higher than the risk of fatalities from a nuclear power plant accident, at least for the case of catastrophic events. The 90% confidence intervals are shown for the risk of 10,000 fatalities or more to remind the reader of the uncertainties in the hurricane and asteroid analyses. The 90% confidence interval for the nuclear power plant risk is shown for 100 fatalities or more, as the risk is essentially zero for 10,000 fatalities. And yes, there is an operating nuclear power plant within 50 miles of New Orleans. To provide a little different perspective on the risk involved, the next slide selects some specific points off these risk curves. In this slide, the mean value fatality risk is presented in terms of the recurrence interval in years, that is, the inverse of the frequencies presented in the previous slide. It should be noted that these are fatalities that are expected to occur essentially during the time of the event and immediately following. No attempt was made in this comparison to evaluate the long-term consequences of the events, such as the onset of health effects that might occur much later in time as a result of residual effects, such as the degradation of the environment. The results presented in this form better dramatizes the high risk of hurricanes compared to asteroid impacts and nuclear power plant accidents. Except for a summary that I will get to in a moment, this completes my survey lecture on PRA. Of course, there is much more to it than what we have had time to cover here. For example, the mechanics of the actual quantification process were only noted, not really illustrated. Much more time is needed to dig into the details of the modeling process. But hopefully you did get a glimpse into the power of PRA and when and why its application is critical to making good decisions about threats to society, especially that class of threats that may not have a high likelihood of occurrence, but if they do occur, could have catastrophic consequences. Also, hopefully this lecture has you thinking about some of the myths about calculating probabilities under conditions of limited information. The key is inferring as much from the available information base as scientifically possible, and then having a way of making what you can't infer a part of your answer. That is, have your answer include a quantification of the uncertainties involved. Let me now close with a brief summary and conclusions. By now it should be clear to you that the principal components of this PRA methodology are scenarios, likelihoods, and consequences. And as we have learned, it is just scenarios and likelihoods, as the consequences are part of the scenarios. A distinct property of this PRA methodology is the quantification of the uncertainties in the results. Transparency of the methodology is a result of the analytical process being rooted in the fundamental rules of logic and plausible reasoning and contemporary systems analysis, with Bayes' theorem being the foundation of the thought process. The probability of frequency concept provides a very effective format for presenting risk results. In particular, undesirable event frequencies in the form of probability of frequency distributions are often chosen as the measure of risk for engineered and natural systems. The application of PRA to low probability, high consequence events for which there is limited information has been its highest payoff. And finally, while methods differ, the steps in performing PRA are well established, and the process has reached a high level of maturity and success. This concludes my remarks. To those of you interested in learning more about PRA, I refer you to the references that are being provided with this lecture. Thank you for allowing me to share my views with you on the remarkable new science of probabilistic risk assessment.